So we have all seen the amazing advancements in generative AI in recent years. And in the field of computer vision, those advancements can be largely attributed to the rise of diffusion models, which have emerged as the state-of-the-art image generators. Those models are trained on billions of data points, which are often scrapped from the internet. And models like Midjourney, DALL-E, or Stable Diffusion offer amazing capabilities. For example, they can imitate images that imitate the art of artists. In this case, can you guess which of the images is generated using Stable Diffusion with the prompt, a forest painting in the style of Erin Hansen? One image is generated with Stable Diffusion, and the other three are examples of real paintings by that artist. So you can take your pick. It turns out that it's the second one. So it very closely resembles the style of that artist. But this is only possible because real images, real paintings of Erin Hansen have been used as a training set of this particular diffusion model. And this naturally raises some concerns. There are currently ongoing legal battles in which artists or media owners want to claim legal justice for the illicit use of their work. For example, we have the court case of artists from California state against Stability AI. This issue also affects large image owners like Getty Images. And with new cases popping up from time to time, the issue is sure to remain relevant in the future. And this legal discussion is far from closed. This is currently a gray area. And what would be very valuable in that context is to have a tool that would help artists and media owners defend their copyrights and intellectual property. So it would be very valuable to have some method, some measure that could answer and reliably answer the question, was a particular sample used in the training set of a given diffusion model? So seemingly fortunate, such branch of research already exists and should provide answers to this question. And this field of research is called membership inference. And membership inference attack work in that way in general, that you select a sample S, you query the target model with the sample, so you interact with the model in some way, and based on the model behavior, you make a decision. Was this model in the training set? Was this sample in the training set of the model or not? And the samples that were in the training set are referred to as members, and ones that were not used are called non-members. And the most important intuition behind membership inference is that machine learning models tend to minimize loss on their training set, so member set. And a very basic example of membership inference attack is the loss threshold attack, in which if a loss of a sample is lower than a given threshold, you mark this sample as a member. And if it's higher, you mark it as a non-member. Now, in order to execute this attack, we obviously need some kind of loss function. So let me briefly say how diffusion models work. In principle, there's first this process of iteratively adding noise to a sample. And in training a diffusion model, we train a neural network to iteratively remove the noise from the added sample. So as Franska previously explained, the loss of the diffusion model is the difference of the noise predicted by the model and the noise that was actually added to a given sample. Okay, now we know what's the loss, so we can try to execute this loss threshold attack. Yeah, so we choose sample S, we noise it to a given time step, we run the denoising network, obtain loss, and yeah. If you do it on a number of samples, you can actually set the threshold that best separates members and non-members. However, the problem is that membership inference attacks fail on large diffusion models. And this is not only the case for this very basic, yet powerful actually, denoising loss attack. This is also the case for other state-of-the-art methods. And here this table shows true positive rate at the allowed false positive rate of 1%. So random guessing in this case is 1. And we have tested those methods on an array of models. And fairly speaking, they are not much better than random guessing. So the natural question is, how can we do better? With the failure of membership inference attack that are executed on per sample basis, we shift to a different paradigm, which is called dataset inference. And now, what we want to infer about is whether a collection of data points was used to train a particular model. And the intuition behind that is that we want to strengthen the membership signal from multiple samples. And in particular, we of course want to answer this question in the context of diffusion models. So now let me walk you through the solution that we have designed. So the first step is to prepare a data model. So we gather two sets of images. The first one, referred to as P, published, are the images that the owner suspects may be used for training a particular model. And the other set, unpublished, U, are images for which we are sure that they were not used to train the model. They can be, as the name suggests, unpublished, but actually they can, for example, be published after the model has been made public if we are sure that it was not retrained, for example, later on. Now, the next step is to extract membership features from each sample from those two sets. And those features should contain the membership information from the sample. And they are modeled after existing and newly proposed membership inference attack. So we have denoising loss, which is this very basic noise prediction loss for a noise sample. And the intuition is it should be lower for member samples. We have the SECMI attack, which in principle works by first noising and then denoising the image one step. And this procedure should introduce more error to the non-member samples. Yeah, we also have PIAN, and here the general intuition is that the ratio of error of noise prediction for noise samples and clean samples is higher for member samples. So another thing that works on this loss minimization observation. And we have also proposed our new features. Multiple loss is a very straightforward one. We just measure the denoising loss at a different time steps for the diffusion model, collecting more information. We have noise optimization, and this attack works by in the following way. First, we add some random perturbation to the noise image, and we try to optimize it in such a way that it minimizes the model loss. And it turns out that this optimization is much easier for member samples. And finally, we have gradient masking. During the denoising process, we mask important parts of the gradient of a sample. And despite this important information missing, the loss is still lower for member samples. So we have now collected a vector of features for each sample. And the next step is the scoring model, which will map those features into probabilities of data points actually being in the training set of the model. So this is a simple binary classification model. We train it in such a way that we divide the published and unpublished sample into train and test set. We train on the train set, obviously predicting the label, and then we use the train model to assign membership scores to the remaining samples. And here, not to waste any data points, we do this little trick with cross-validation. So we repeat this procedure for multiple folds of data. So in the end, all data points are assigned some membership score based on their features. And higher score corresponds to the higher probability that this image is in fact a member. So was in fact used in training the model. And now the last step of the pipeline is the statistical testing. And here we compare the distributions of scores we obtained in the previous point for published and unpublished samples. And this is a two-sample, one-tailed Welsh t-test, which compares the means of the distribution. And the H0 of this test is that the score for published samples are lower or equal to the scores of the unpublished sample. The outcome of this statistical test is a p-value, and if it's below a certain significance threshold, which we can set very strictly, like below 1%, then it gives us a basis for rejecting the null hypothesis, which would mean that the scores for published data are actually higher for the scores than the scores for unpublished data in a statistically meaningful way. So what this test gives us is, based on the p-value, we obtain a decision. And if the p-value is lower than the significance threshold, we can actually mark the set of published images as being used in the training set of the diffusion model. So let me recap the end-to-end solution once again. We collect two sets of images published about which we want to learn whether they were used to train the model or not, and unpublished, about which we are sure that were not used. We extract features from each sample that should contain information about how likely is it to be a member. Then we train a scoring model that maps those features to the probability of being a member and use it to assign scores to each sample. And finally, we use statistical t-tests to compare those two distributions. And if we obtain a low p-value, then we can mark the published set as being used in the training of the diffusion model. Now I will discuss our results. And we have tested this approach on an array of models. So we have experimented with models trained on ImageNet with varying resolution. And this is a case of class-conditioned generation. But we have also experimented with models trained on the COCO dataset. And in this case, we have varying text-conditioned image generation models. And we have also trained, for reference, unconditional generation model. So 8 models in total, all trained on large data sets. And the outcome result is that CDI is able to successfully identify collection of data points that were used in training the model. These plots show decreasing p-value with the growing number of samples collected in P&U. And here we can see that for models, for one of the models less than 100 samples is enough to reach a statistically meaningful conclusion. And for the more complicated model, more samples is needed to go above this below this significance threshold, and 10,000 samples in the most below 10,000 samples in the most extreme case. Here I wanted to show that the features that we introduced, so these new membership inference attacks, actually make a difference in the most challenging cases, because, for example, for the UVID model that works on a resolution of 512 pixels, it lowers the amount of samples needed to successfully detect the copyrighted data collection from 12,000 samples to 2,000. An important feature of this CDI pipeline is also that it's resilient to false positives. And what this table shows is the outcome of t-tests for 10,000 samples in two cases. So in the row referred to as members, the published set was actually used to train the model, so it contains member samples, and we achieve very low p-values, well below this significance threshold. However, when the published set was actually not used to train the model, so it contains no members, the p-value outcome of the test is way above the confidence threshold, significance threshold. So there is no basis to claim that p was used to train the model. And lastly, it's a little bit unrealistic to expect that all the data points in P were used to train a particular model. And in reality, what can happen is that the internet crawler just missed some data points, or they were discarded during sanitization. But luckily, CDI is able to detect if a data collection was used in training of a model, even if it's contaminated partially with samples that are actually non-members, that are actually not used to train the model. And in this plot below, the contamination ratio is the ratio of non-member samples in the p-test. And we can see that for this particular model, if 40% of the images in the published set were actually not used to train the model, just the remaining 60%, we can still detect the use of this collection if we have somewhere below 3,000 samples gathered. Yeah. So CDI also works in that case. And to sum up, let me reiterate the most important concepts from this presentation. So very importantly, current membership inference attacks are not evaluated in a realistic way, and they fail on large diffusion models, which are actually responsible for those beautiful generations that we saw at the beginning. And with the failure of per sample approach, we shift our focus to dataset inference, so inferring about data collections to strengthen the signal. And finally, our pipeline, which consists of feature extraction, training, and scoring with a scoring model, and finally a statistical test, is able to reliably answer the question, was a particular data collection used in training of a particular diffusion model, and thus constitutes a valuable tool for artists and media owners. Thank you very much for your attention. And